Okay, welcome to episode 3 of Gravitational Waves in a Nutshell. We are trying to find out how you translate in a nutshell in French. So far, the best suggestion is Ricardo Sanchichi, but maybe it's possible. It's possible to do better. So if you have something, let me know. So recap from last time, as they do on Netflix. We saw that gravitational wave detectors, all of the current ones, practical ones, realize this idea that gravitational waves create a tidal motion of masses. You want to detect that. To do that, you need to realize a free fall experimentally. LIGO and Virgo do that with suspensions, with pendulums, where the free fall is effective along one direction and at a certain frequency range. That creates a lot of problems for interferometry and makes for very sophisticated instruments. LISA, same thing, needs to create free fall. It does so by following free test masses that are really falling in space, but again, only along one direction, which is the direction of measurement across the spacecraft. Pulsar timing arrays, well, you rely on on celestial free fall. Okay, the Earth around the Sun and pulsars, and really you go to very large, very long time scales where motion is slow, and also the effect of gravitational wave is much bigger. Then we went back to theory, looked at the generation of gravitational waves, and derived in a somewhat hand-waving fashion the quadruple formula by a two-length scale expansion, where there's a background term, and the rapid variation of gravitational waves creates locally a curvature for the background metric. This approach also gives you the gravitational wave energy momentum tensor. And finally, with 5 and 7, we went back and to create adiabatic waveforms for inspiring binaries, which are based on formulating the energy and computing the flux of energy into gravitational waves, and then matching the two so that the loss of energy creates an evolution of the separation distance, the orbital radius, or the frequency, as you wish. To lead in order, we have what we call Newtonian waveforms, which have just the Newtonian energy for the binary and the lead in order quadruple, but you can augment that with post-Newtonian corrections. I just showed you complicated formulas. Next week, we'll try to see if we can derive some of those. However, there's a big industry in making these waveforms, and they are very precise, very accurate, and can be used for detection and parameter estimation so far in ground-based detectors. Okay, so what's in one of these? What's really in one of these waveforms? So this is a simple one, actually. So I need to do it, this way. As we were saying, the long adiabatic phase is characterized by a locally sinusoidal, just orbital motion dependence. You get gravitational wave emission at twice the orbital frequency. As the energy is lost, the orbit shrinks, you get increasing frequency, and as we saw from the quadruple formula, also the amplitude increases. And then you go into merger, so there's a change of scale here, right? So this large oscillation here is here depicted as much smaller because the merger is quite is much more luminous. It's only a few cycles, and it gets more complex if you have spinning black holes with non-aligned spins, orientations. After the merger, when the black holes form a single horizon and a single black hole, then you have a phase of ring down where it's the fundamental and the dominant subdominant oscillation modes of the black hole ring out and again lose to gravitational waves and until you're back to nothing. Okay, so that's the description. What physics, okay, can you extract by detecting and characterizing this waveform? So the first thing one could say, just by looking at everything that goes into computing this in spiral, is what parameters you have. So for a circular binary, you have the two masses, you have two spins, which bring 3 degrees of freedom each. You can think of those as the amplitude of the spin, which in a black hole can go up to the square of the mass in geometrized units, because then you become an extremal black hole, and that's all you can do, right? And two orientation angles for each spin. Then you have to decide to set the position in the sky with respect to the detector of the source. So two angles, latitude, longitude, however you want to do it, and the luminosity distance. We see also either next week or the last week how black hole generation works on a Lemaitre, Friedman, Robinson-Walker background. And we'll see that it is the proper cosmological luminosity distance that sets the scale, the amplitude of the binary. Then you have a couple more angles, because you have to see, so you know where it is, but you need to see the angle of the angular momentum of the orbit with respect to you. So that's called inclination, iota usually. There's a polarization, which is a rotation and sets the polarization of the waves. And then finally you have two offsets. One is the initial phase of the binary at a reference frequency or reference time, and one usually is taken as the time of coalescence, so the time of the merger. So then various combinations of these parameters actually matter the most. As we saw, the inspiral phasing really is a function of this chirp mass, which is a combination of fractional powers of the two masses. The fractions come from Kepler's law, really. And this is the parameter that's measured the best, okay? Especially for full ESA, it would be measured to a part in 1,000, a part in 10,000, very, very, very well. It affects both the strength of the waveform and the progress. However, the total mass and the final spin, which is a more complex function of the two spins, are the ones that affect not the inspiral phase, but the merge and the ring down. At that point, it's forget about Kepler, right? It's very nonlinear dynamics. The two things are merging, and it's really the masses that matter there. And for sure, the total mass is which is the sum of the two masses minus some percent that's lost to gravitational waves, is what rules the ring down. Then we saw a few more things. So one is that if you fix the mass ratio, eta, remember, is this symmetric mass ratio, m1 times m2 over m1 plus m2 squared. If you fix that, you can renormalize, not reparameterize the entire waveform in terms of time over total mass. That's the only scale there is. And then that's what they do in numerical relativity, right? They don't say, I'm going to simulate a black hole binary of 10 solar masses, because it doesn't matter. They just, all the units are in terms of total masses. Now, spin components, there are 6, as we saw, but there are 2 combinations that really affect the waveform most strongly. There's a parallel, the component that's parallel to the orbital angular momentum, and it comes in weighted by the masses, and you see dotted into the total angular momentum. This comes at leading order into the orbital energy, right? It's a nonlinear effect in GR that changes the speed and the progress of the spiral. Instead, the components that are parallel to the orbital plane, not the momentum, so perpendicular to the orbital momentum, are the ones that cause precession of the spins due to spin-orbit and spin-spin interactions. And precession would manifest in the waveforms as longer-term modulations, basically. Oscillations. That's very interesting, as we will see, if we can detect this effect. Amplitude, we said mass over luminosity distance. There's a geometric factor due to the fact that the gravitational wave effect is transverse to the direction of propagation, and a detector like LIGO has an obvious 2-axis structure. Okay, so the combination of those two is usually expressed in terms of antenna patterns. So F plus and F cross. F plus would be more or less the sensitivity, or the coefficient that multiplies the plus polarization in the frame of the detector. The cross the other one, the cross polarization, and put together you find a basically omnidirectional sensitivity pattern with a few nulls for a single detectors, but this omnidirectionality is what makes the geometric sensitivity to position kind of weak for LIGO and Virgo as it will be for LISA. However, there are more tricks to play, and LIGO in particular has time of flight differences, right, between the detectors. And massive binaries, as a rule, will be more visible, right, because the chirp mass is larger, the total mass is larger. However, they end earlier. So this is a very rough rule of thumb for the end of the signal. That's just the last stable orbit, the LSO or ISCO, sometimes one calls it in GR, in dimension full units is of order 400 Hertz for a 10 mass total mass binary. And now, yeah, I was saying that position you determine mostly by triangulation. But I wanted to show you a little bit more about these amplitude patterns. So that's what the antenna patterns look like. Antenna functions, that's theta and phi position in the sky. Psi is the polarization of the signal, which is arbitrary, right? You have to decide how you set your axis. And that's what a single detector does for both of them together. And that's the result of adding more detectors to the international network. So Hanford and Hanford is Washington State, right? Hanford and Livingston give you some holes, some nulls in the sky. If you have Virgo, you do better, but you still have a factor of, well, maybe 10 between good directions and so on. If you start adding, let's see, what I is India, like go India, or you add, you should have the Japanese detector here somewhere, you can basically get optimal sensitivity across the sky. Okay. If I can't what, sorry? Let's see. There may be a degenerate one. 1, 2, so 6, 8, 11, 13, 14, 15. Yes. Yes, it's 15. It's 15, yes. I'll change it before there's one that you get for free, so maybe that's where and I'll show you later. That's probably why one says that. Okay, let's do data analysis in a nutshell. So this was a bit of propaganda, right? I gave this lecture to a very different audience, but basically the fact that the data you collect has signal and has noise is almost everything that you need to know. Okay, everything comes down from that. Now you need to characterize the noise and you need to model the signal. And there's a caveat that you never get quite the signal, right? The instrument also gives you a transfer function of the signal into the data. For LISA, it's quite complex because it's this synthesized interferometry that creates, takes one pulse of gravitational waves and give you 16 pulses in your response. For LIGO, it's a bit more direct, but it still involves a multiplier for the amplitude that needs to be established experimentally, and also phase delay that needs to be established experimentally. So that's that would be calibration, and calibration is something that has its own working group in LIGO Virgo, and that has that working group, you know, fighting with the data analysts, because the data analysts say we want 1% calibration, and they say no, we're going to give you 3%, and so on. Okay, so but let's be a little bit more formal, because this formality that actually pays a lot, and let me show you two models. Okay, so these graphs here are what's known as either probabilistic Bayesian network or a constructive model. And the idea is that You start, what you measure is at the bottom, the data in this case, and everything that makes it, that contributes to make it is above it with arrows. So you can use it in two ways. If you want to simulate your data, you have to start at the top, simulate at the top, and then go down. If you want to do inference, you start at the bottom and go back up. And every arrow has a conditional probability associated with it, although in some cases it can be simple. So this one is almost trivial. It's saying there's noise, nature makes noise, there's a certain probability for each noise realization. The data is just equal to the noise. So the conditional here would just be a delta, basically. So this is one hypothesis. There's nothing, just noise. You want to compare that with one where, let's say we have only one possible signal in the universe, because I don't know, there's some very perverted theory of inflation that creates lots of this, okay? Little down blip, up blip. In this case, there's no probability distribution for the signal. There's this one. They just sum up again, would be very simple. How do you compare these two things? Signal plus noise, and this is what you see. How can you tell that here you do have this guy? Well, you need to be able to model the noise. Okay, and if you assume that the noise is Gaussian, so that basically every single sample that you get over a long term has a Gaussian distribution, then you can write the probability of any noise realization. Doesn't choose a length, right? A year is going to be, I don't know, 30 billion samples, 200 billion samples. You put them all together, the probability of having just that realization of the noise is going to be effectively an integral of the Fourier domain, the Fourier transform, divided by the power spectral density of the noise. Okay, so the spectrum that you measure, and that is also a metric of quality for data. So now that means that I can compute likelihoods for the data in both models, and I can take a ratio of the two likelihoods. So in one case, I will set the noise equal to what I see. In the other case, I will set the noise equal to the data observed minus the model of the signal, which is in this case is given. And you end up with integrals like the one I just showed, weighted power, basically, by PSD. And although you know, these two plots look very similar, actually they are quite different in terms of the total power that's embedded in them. In one of them, I've subtracted out the signal, and so this ratio, the two probability, is actually almost 100,000 here. And this would be a signal to noise ratio. You can take this as a definition here, around 5. Okay, so this is the game effectively, right? Compare models using your knowledge of the noise. There's another interpretation of this, which is the one that historically was taught earlier, is that you can kind of decompose these products here and these norms into basically correlation products of the signal with the data. Okay, and the effect of that is that the idea is that if you take a product of the signal with itself, an oscillating signal where it's both negative or both positive, you get pluses, and so this integral will be positive. But if you take a correlation product of noise with a signal, you basically get 0. Okay, so then you can concentrate on this term, and that's what you'd call the match filter. But in effect, it's really the same thing as weighing the noise content of the data, and the data is minus the signal. This interpretation, though match filtering, is somewhat is intuitive, because then you can take the 15th parameter, right, the one I was and time, and say, okay, I know there's just one signal this shape, but I don't know when it happens. Okay, and then you can say, okay, I'm going to slide, okay, my signal against the noise and compute the correlation here. It would be the purple or the blue signals, and you see that it peaks when the signal template, you'd call it, because it's a model for the signal, is aligned as best as possible with the data, the noisy data that you observe. And then it goes back down. And so you'd build a detection, you call it now a detection statistic, the product of two these things, which remember comes from the weight in the data. You can find out on average what you're going to get on average over noise realization, and you call that the optimal signal to noise. And you see it's a power integral of the signal alone. And you can play the game of saying, okay, if I do this if I do this detection statistic, if I compute this thing by sliding my signal against the data, when there's no signal, I'm going to get 0 on average with some spread. If I do it when I do have a signal, I'm going to get a value that has a mean that's positive, also with some spread. And then you can say, I'm going to take a level that I get very rarely, say once every year, when there's no signal, and I'm going to take that as a threshold. And if I get more than that, I can say that there's a signal there with a false alarm probability of less than 1 over a year. Okay, so that's the basic scheme. Any questions so far? Or yes.
That way is two formula on the first one on signals to noise ratio.
Yes.
And it looks like it's linear on the data.
It is, yes.
And on the second line, you get 1 over S, which is, I assume, the Bose spectrum of the data.
So here there's no data. The spectrum comes from the data, but it's not the data you're analyzing to see if there's a signal. It's and it's true. I left something out here. This should have a correlation kernel. Since this is time domain, I mean, you do need this noise weighting in the time domain. It would look like a c to the -1 a correlation. So maybe I should adjust that. But it complicates this formula a little bit with two time integrals and so on. This would be what it looks like in white noise, let's say, if your noise is white. But they're different things, right? So this is your detection statistic. It's linear in the data. You're sliding your template against it and seeing where it peaks. This one, you get a square, right? So you could take the square root of this and get something that's linear in the signal itself. It's the square root of this is the average of that, let's say. It's the average performance.
So in practice, you have a finite time of data.
Mm-hmm.
So do you take Fourier series instead of Fourier integrals of frequency?
Yeah. You do. They're all finite dimensional things. LIGO probably uses segments of maybe 4 minutes, something like that, or maybe 256 seconds, because so far all the signals are going to be shorter than that. And it would use many segments around it to estimate the spectrum, to estimate the PSD averaged out, so that it's a bit smoother. And then it's all finite data. With Lisa, for some things you need to consider the entire 5 years, 4 years, 10 years of data. It's unclear whether you can do one big FFT, not so much because there's too much data, but because the noise is not stationary. So you'll need to either break it into pieces or do some more sophisticated description that takes that into account. But if we had a perfectly stable instrument, you could, in principle, do one big FFT for a signal that's as long as the data set itself. Okay.
Even your strategy that you expect to have false positive.
Mm-hmm. Oh yeah. It's we're going to talk about that. Okay, in practice, let's see the use of these things, because they get complicated quickly. There's more to it, right? Even if you describe it formally in a model. So the noise in the noise only model. Okay, so it's not just that the noise itself comes from a distribution where you know the spectrum. The spectrum itself needs to be estimated and can change in time. You may be able to put in some hyperparameters, right? Parameters that rule the spectrum itself and estimate those. Also, you have glitches. What's a glitch? A glitch is something that happens in the instrument that shouldn't. Every experiments have them. Actually, I can just show you. These are examples of some glitches with an artistic interpretation on top of that. This is time frequency diagrams, right? So time this way, frequency going up this way. This is the first event. These are things that are seen in time spectrum from time to time. And the thing is, okay, they don't look like the signal, but if you just feed these into this Gaussian formalism, they're going to give you a big detection, right? Because you don't expect the Spanish Inquisition, no, you don't expect noise like that. So you add them to your model, let's say, and a signal model would have glitches, would have unknown source parameters. Okay, so you need to be prepared to detect a variety of possible spirals. And you have also an uncertain detector response calibration. As I said, you may get 102% or 97% of the actual amplitude, and you may get a frequency dependent also phase shift that alters your gravitational waves because of the complex interferometry that we were talking about last week. So here I wrote it just as a multiplication, but you can think of that C as an operator. Yes?
So about the glitches, so in practice, you could remove the data where there were glitches or subtract them. So,
yes.
So what do you do in reality?
Both. Okay, so it used to be, so these glitches, you see them in your strain output. Many of them you will also see in the auxiliary channels. Okay, so you may see a feature in the strain output, and there may be a feature in the interferometer that is monitoring the tilt alignment of one of the mirrors. So those are, people call those explain glitches. And at that point, if you have a physical mechanism, you can just look at the auxiliary channels and use those to cut out data. Okay, you want to be sure that that the auxiliary channels are not triggered by a real signal, but otherwise you can do that. However, what's happened, I don't know if I have a plot later, but as the interferometer gets more and more sensitive and there are more and more events, even more than one detection per day, there are some detections that have a glitch on top of it. Okay, and if you can excise it because it's sufficiently different in frequency, at that point you do it by trying to model it either phenomenologically. I think there are some actual physical models for some mechanisms, and then you take it out and you're fitting it in a way simultaneously with the signal. So it's it was considered too dangerous to do for the first detection, but now it's more routine. And the double Newton star that had the measure that the observed counterpart had in one of the interferometers had a glitch on top of it that needs to be removed to have the best parameter estimation. You can leave it there, but it biases things, of course. Okay, so this is the evolution of if you give talks for many years, you must have these slides that come from that have a provenance that come from a talk and go into another one and then into another one. And so this slide actually comes from talks that I was giving, before 2010. So it used to be a slide without a happy ending, just with a hope that this is what we do, one day we'll see something. And then I changed it to actually reflect the fact that this process works and worked. So, okay, so that's the theory, right? You do a filter, you do this sliding filters with theoretical templates to account for the fact that you don't know the parameters. LIGO uses maybe 200,000 different parameter shapes. You want to space them out so that you catch most things, but you don't do too much work, more work than you need. But then there's more to it, right? You need to estimate the spectrum, so that requires spectral estimation. You need calibration, and then because things are not ideal, right? You wouldn't. One of the reasons LIGO was built in 2 is that you wouldn't believe a single detector, no matter what you saw. And so you request coincidence, and consistency, meaning you want to see this peak of the signal to noise at compatible times. You also want to see the same shape effectively in the two LIGOs, which are parallel, and in the two LIGOs in Virgo, which have an angle with respect to them. So this is already out of this purely Gaussian world. Right? Here you get these Gaussian triggers, let's say. Here you do a cut requesting consistency. Then you can apply data quality cuts, look at all these auxiliary channels, and this would be the glitch rejection. And you can estimate statistical significance. And how do you do that, right? Because as soon as we leave the world where we believe our noise sampling distribution, you don't have an analytical distribution for the noise. You cannot compute how many false alarms you'd have because you don't believe that the distribution of the noise is really what you put in the game. So what's done is to estimate the background empirically. And the main technique, there are two techniques that are equivalent, but perhaps the easiest one to understand is time slides. The idea of time slides is that since we're doing coincidence between two detectors, you can look for coincidence between something that you get now and something that you get 10 seconds later. There's no way that's a gravitational wave, okay, just because of causality. So it must be a random coincidence between two triggers that you get out either because of noise statistics or because of noise glitches. So you do many of these time slides, and that builds the background of your detection statistic. The hypothesis there is what? That you have that your interferometer is in a homogeneous state for the duration over which you take your time slides. Okay? If the noise changes, you start to get into problems. And then, okay, detection checklist is the idea of checking many different things and so on. And finally, you can either claim a detection, or that's what I had in the slide before, get an upper limit. Just look at the loudest thing that you did. So that's what this thing looked, again, for the first detection. The search was over binaries with masses below 100 solar masses. It used 250,000 templates, so different parameters shaped. It augmented this match filter, the SNR, with a chi-square, meaning it's a way of doing a veto from the signal by seeing that every frequency component contributes as it should. And now this empirical background, so the time slides were done so they, in order to create a synthetic extension of a background for 600,000 years, effectively. Okay, and so one gets a false alarm rate of less than 1 in 200,000 years. I think this is just divided, I think, by the number of different ways that different analysis pipelines that we're looking for the signal, and that is equal to a false alarm of 2 × 10⁻⁷, so 5 sigma. Now, this is actually not limited by was not limited by the strength of this trigger. It was limited by how much background you could build, and that was limited by the duration of the experiment. But if you were to believe the Gaussian, okay, so let's look at here. So this is a distribution of the number of events as a function of the detection statistic. This is an R, effectively. It's a different. It's a natural logarithm, so it's multiplied by a number or something. But so a purely Gaussian distribution will go flat down, and you see that you almost get it. The black is somewhat technical, but is the idea that when you do the slides, you can either include the signal itself, the event, or you can exclude it. And there were huge philosophical debates about it, whether to do it. And but if you do exclude it, you almost get the Bayesian, the Gaussian distribution, and this guy has huge significance, right? You'd have to compare it to something that is way down below the screen. 5 sigma, however, was felt to be enough. Yes?
So the fact that you have these different templates, are they kind of similar, but then you're changing the parameters within them, or are they like fundamentally different things?
they just differ by the parameters. And for something like this, you can cut down on those 15 parameters a lot, because some just affect the apparent amplitude. Let's say some are taken care of by that integral, like the sliding, the initial phase. Some you just neglect. For instance, you may say, okay, we do detection without spins, or just with the effective spin. With just the effective spin and not the spin tilts, then you can bring those things back when you do parameter estimation, but not for detection. Okay, so examples of this was O1 and O2. So for the first runs, a variety of different shapes. These are all black holes, I think. So you can see a bit here the variation in templates. And I think the two plots are all Livingstone and Hanford with the clean data with the recovered theoretical shape on top of it. And yeah, there are a few things that may be glitches, or maybe, you know, some kind of oscillations and so on. But that scheme worked very well. Okay, so parameter estimation now. Same story, right? But now we envisage a variation of a signal as a function of two parameters. So this is my little model. It's almost glitch-like, actually, the signals, but it's you can change the frequency and you can change the envelope. Okay, so a sine and an exponential. The game of parameter estimation, again, is to find the shape of the signal that, when subtracted, minimizes the apparent noise that's left in your detector. This would be the scheme. And since, you know, things get complicated fast because of all these effects that come into it, now you have to worry about calibration, you have to worry about the noise estimation and so on. You have many unknowns that come into play. Well, we turn to Bayesian inference, okay, and which I summarize here. I'm not going to try to presume to teach you Bayes, but basically you have a prior distribution for the parameters of the source. Here we assume we've detected something, okay, it's a confirmed detection. We have a prior for the parameters. Our prior knowledge is updated by the likelihood of the data as a function of the parameters. And there's a normalizing constant, which is the marginal likelihood, so just the integral of this numerator. And this is the simplest Bayesian network again. And the trick is from the data to go up to this theta by marginalizing. So I should do it here, otherwise I don't point well. By marginalizing over the parameters you don't care about. This is one example of this posterior of the two parameters, frequency and envelope decay for my model. And you see, you map noisy data into really a distribution, probability distribution for the two parameters. And there's something that, is it here? Okay, sorry, like this. The Fisher matrix, right, is something that comes up often in parameter estimation, especially in cosmology. What is the Fisher matrix? Fisher matrix is just really a Gaussian or normal approximation to these shapes. And it is a function of the first partial derivatives of the signal with respect to the parameters. And this product here that I wrote with the parentheses and a bar is just these noise integrals that we were looking at before. The thing is, it's a leading order approximation. It is not a function of the noise, even of the noise realization. That comes in as a correction of at order of 1 over signal to noise ratio. So if your signal is not very loud, just by changing the noise realization, here I kept the same signal and I computed the posteriors, you can get a variety of shapes. Fisher alone will give you just an ellipsoid. Here you can get some more fun, basically. Yes?
The sampling of the parameter space is done with the max chain.
Oh yeah, I'm getting into
Yes.
Yes.
Okay.
So for something simple like that, if you have only two parameters, you can actually do a grid sampling. That's what I did here. I just spaced around and computed the likelihood over the grid. Beyond 2 or maybe 3, you can't afford it, right? And then you go to stochastic methods. But to show you how this looks in reality, and again, let's look at our first event. You get this kind of you get histograms for your parameters. Usually, it's hard to plot them more than 2 at a time. And you plot these are called credible regions, right? Since these come from the base and posterior, they're not confidence. Their credibility, they're where you concentrate your belief, really, your rational belief about the system. So these are the two masses. You see this cut here is because M1 is always taken to be larger, I guess, than M2. The different colors are 2 different families of waveforms that come actually from rather different assumptions. These are the final black hole parameters, final spin and final mass. These were the luminosity distance, 400 megaparsec, and this inclination angle. And these were the spins where there was, well, effective spin actually for the system was compatible with being 0, so with having very little spin. And there was really no information about any precession. This was a signal with few cycles. This is sky position, and you see it's so if you do the geometry and say triangulation for the 2 LIGOs, you get a geometry where from a certain delay between the 2, there's a circle in the sky that could have yielded that delay. The fact that the circle is broken is by the amplitude between the, is that right? Yeah, by the inference on the amplitude due to some partial knowledge of the angles of the system. Okay. So you're asking about stochastic. So again, I have this slide calls you to guess, not to guess, to be able to recognize this gentleman up here. So my friend Stas, who's Russian, said that's Landau. And no, he's not Landau, but maybe equally eminent. So who are those? That's Feynman in the middle, yes. Recognize this guy? Maybe one of the top 3. That's von Neumann. And that's Ulam. Okay, why von Neumann and Ulam? Because Monte Carlo actually goes to von Neumann and Ulam, not Feynman, and has there are these stories that go about it. But apparently, Ulam was sick in bed, and he was doing this solitaire, which is kind of automatic. So at some point, he got tired of doing it. Say, how about could I figure out how often I would win when I do the solitaire without actually doing it, because he was a physicist, and so he realized that a machine like the computers that were being built at the time, 46, that's pretty early, could easily do something like that, right? And from that, so he spoke to von Neumann. They realized they could use that basically to make hard integrals, let's say, by just sampling a function randomly. And the thing that works well here is that the accuracy does not depend on the number of dimensions, just depends how much that function oscillates over all parameters. So that's the basis of Monte Carlo. Unfortunately, that's very inefficient when you go to high dimensions, even if you have this problem of square root. And why? Because if the region of interest is small compared to the range of the parameters, as is generally the case, well, the ratio of the volume of a box to the ratio of the volume of a ball of fixed diameter, this d, goes like a it's an exponential. It's a d to the d. You lose very quickly. So in 1953, there was the crucial. I like adding this to this lecture because I really like these things, and I end up doing a lot of stochastic sampling in practice. So it's just fun to look at the history. The crucial suggestion was that instead of trying to integrate, of doing this integral, you go basically range over the prior and then compute your function and a probability distribution. You really want to sample, to have a measure that's proportional to the probability that you want itself. So in this case, you'd only sample inside the ball. And since this was done for statistical physics to start with, you know, maybe you sample a canonical ensemble, and now you do the same Monte Carlo, but you want your x's, the point where you sample the function, to be distributed according to this canonical distribution. So how do you do that? Well, more faces. So these are, I'm telling you, are Rosenbluth. It looks a lot like Susanna. Look, if you don't remember, Teller. Okay, and not looking too evil here. And Nick Metropolis actually looking rather evil. And so the classic paper was Metropolis et al. And they came up with the Metropolis algorithm. Okay, so the interesting thing that's here is we were talking about I think mistaken attributions or so on, but the Metropolis algorithm is probably the Rosenbluth algorithm, right? Teller had the idea of sampling following the distribution, and probably Rosenbluth, maybe the two Rosenbluths together, actually, who was a husband and wife, came up with the idea of the Metropolis algorithm. Metropolis was the computer builder, right? He owned the cluster, he owned the computers. He was very good, but not an algorithmicist, okay? So, and looks, you know, dangerous there. Yes. Yeah, please. Can you, there's a question from the audience? Can from online? Can we hear it, or maybe can be read?
Maybe it disappeared.
Oh.
Okay, what's the name?
Good. So you Metropolis algorithm, you know about it these days. So you're wandering through your parameter space. You make a proposal of jumping, and then the proposal can either be accepted or not. And this scheme gives you a guaranteed in the infinite limit of achieving the probability posterior, the probability distribution that you seek. I don't have. I could have shown you this website, but I think we should move on just for speed. The result, this is beautiful actually. It's a website that animates this thing for many different algorithms of increasing sophistication. Right now there are things like Hamiltonian Monte Carlo, no U-turn sampling, Langevin, I think sampling, and so on, that all use either physical metaphors or very cool tricks to explore parameter space more efficiently. So that's that website has a nice visualization of that. In practice, you get clouds of points. Okay, so and I will show you some of those clouds, not cloud chains of samples of your parameters that approximately come from the distribution you seek. In our case, the posterior distribution of the source parameters given certain priors for them and given the data that we observe. Okay, so let's go to real data. Let's go to LIGO Virgo. These were actually the sensitivities in the runs, the 4 runs so far. These are expressed a binary Newton star range. How far you can see binary Newton star merging with classic masses. I think it's 1.4 and 1.4 solar masses, optimally oriented. I think that's how it's computed. And you can see, you know, a factor of 2 improvement almost in LIGO Livingstone, which is the best so far. Virgo has been improving also. So that means that these late runs have lots more events, okay? And that's the best here. Yes? Why the difference?
Yes.
In range? Okay, longer range means less noise. So this is partly a function of the design of the instrument. Virgo is a bit different. It may be a little, they may allow for less laser power. I'm not sure. Partly how successful they've been in realizing that design sensitivity, and that because it's not like, you know, you buy this thing, you turn it on, and it works with your fundamental noise. It's horrible usually when you turn it on. So they have to beat down all these noises and before you see the fundamental noise, there are all these technical noises that are things like, okay, when I'm not perfectly aligned, when I push to align and actually introducing noise, the some viscosity, residual viscosity in. So it's different groups of people working in different sites, although they travel a bit, and they've been more successful in Louisiana. Maybe the environmental conditions are also better there in terms of the residual seismic you have and the atmosphere and so on. So every instrument is, you know, an individual. So I think the Virgo group is very aggressive, so that it'll continue to improve. I think the actual design sensitivity is much better than this. And also Virgo is a bit disadvantaged by this measure because it was built more as a lower frequency instrument with better seismic noise rejection. And the Newton star measure weighs the higher frequencies more because that's where most of the Newton star signal is. But that's a historical measure because you expected lots of Newton star signals because we knew we had Newton stars in the binary in the galaxy, right? And black holes, who knew? So the LIGOs were thought as Newton star instruments. But okay, so this is the best theory so far. I think these are the 90 events that have a detection probability larger than 1/2. Most of them actually have a detection. So that's not the false alarm rate. That's turning the false alarm rate into a probability for a given event as you get it. Most of them have a higher one, have 99% or more. And so that's the first guy, you know, up there, 36 and 31 solar massive, building 36. I circled some things of interest there. Maybe I see them better here. So the ones that are blue, light blue, are the Newton star binaries. 2 confirm double Newton stars. The first one was the very lucky one where you also saw, you know, electromagnetic fireworks. Another one later, no counterpart was seen. 4 systems with a suspected, 4 Newton star black hole systems. 1 system that's somewhere in between with a mass of 2.8 for the lower component. That's much heavier than we think Newton star should be, but lighter than black holes should be. A few other things. I also circled some of the black holes where, let's see what was interesting here. Some of these black holes in the 50 to 100 solar mass range. That's a range where we didn't expect black holes could form or should exist because of something known as the pair formation instability in supernovae. The ones that I marked with S are black holes where there's clear evidence of spins, so posteriors that don't include 0. So, and I can't tell if this is cool or not as a visualization. I don't know about the symmetry. Maybe to just do it one way. But this shows you maybe the one thing that's most obvious here is how much of a new window, right, of a new channel this is. The EM black holes had all in general much lower masses, although there's some overlap. Neutron stars are down there, but the other thing that these later runs showed is that intermediate mass black holes, so black holes that are heavier than 100 solar masses, exist, just because there's the result of merging to like 250s or 270s and a 6 and a 7. So it was unknown whether they existed, and we didn't really have any signal for that. Okay. So nothing. It's just arbitrary. They did it to have this nice shape. Yes.
Stars are Newton stars known
in the galaxy, for instance, as pulsars, mostly as, and some as recycled Newton stars, right? Bursters, things like that. Maybe the ones we have masses for. We have good masses for, because even in in a pulsar, you have to have two masses. You have to have, for instance, to be able to detect a Shapiro delay. It's not easy. So unless it's a representation, I don't know. We should ask Aaron Geller. Okay, so do we want to take an early break, or or go another 15 minutes? What do you think, boss?
You feel
No.
maybe break.
Yeah, okay, let's do a quick break. Yes, yeah. A microphone. Speak into the thing.
So there are templates. I don't remember. You said how many. So the templates are a number of waveforms,
Yes,
I guess,
yeah.
generated. And how many of them there are? So how many of them do you use? Do you make interpolations between them
No, you don't
in
need to make
parameter space?
interpolations. So the initial searches, I don't know if they raised it. Maybe someone knows here if they raised it for the later runs. But for the initial runs, it was of order a few 100,000, right? 250,000 shapes. You try to place them so you don't have holes. So you can do a criterion where you say, okay, so if I have my templates in this space, if I put a signal at the worst possible place, how much SNR do I lose because you're not perfectly aligned and you lose a little bit. And you say, okay, we can lose like 2% or 3%. They're placed based on a limit like that. And
so, do you scan the full 15-dimensional parameter space?
No, the detection templates are laid down along a smaller dimensional place that preserves most of the detection. So if you, as I was saying before, some dimensions you get for free because distance, okay, just going to be stronger or weaker. Time, well, you're doing a frequency, you're doing Fourier transform anyway, so you have that. You do the transform, and the result is all the possible times, more or less, right? Phase, you can actually show that you almost get it exactly. If you shift the phase of the binary, it's equivalent to changing the phase of the Fourier transform. So you just look at the modulus. Mm-hmm. So some you get for free. Sky position you almost get for free. I mean, because it mostly falls into the amplitude. So I think the actual template banks are either 3 or 4 dimensional.
I see.
So it's really the two masses, the effective spin, and in EOB, what's the fourth one? Probably another spin parameter. That would be the one that. They all start at the reference frequency, so they're all computed from either 10 hertz or 20 hertz, where you know that there's so much noise that basically you use the fact that you end up into noise. Okay, so it doesn't matter that you don't have a template at 1 hertz where it will be lots of cycles evolving very slowly, and then they're all thrown together. And then there are more sophisticated things. Like some searches actually do something like a PCA on the templates themselves, and then break them into linear components. Use the components to do the sliding, and then assemble it back into actual things. There are many games that are possible, but the basic ones are there. Lisa will be harder, right? So in Lisa, there will be situations where we can't afford to have template banks because there are too many signal shapes, and then you have to decide what to do. You could do a stochastic search, so where you build a scheme where you hopefully end up on the right shape. You can do a hierarchical scheme where you where you start with simpler templates that don't get all the power but get you something, and then refine. You can break the data set into parts, and shorter time means fewer signals because there are fewer cycles, so there's less freedom to change them apart, and then try to put them back. So, Ken is one of the the practitioners of these games. Okay, coffee. Online audience will be back in 10? 15. Okay, 11:15. when I'm introduced to strangers, it's usually looks good to say I'm an astrophysicist, because they start thinking, they think I'm thinking about black holes all the time and neutron stars and so on. And of course, if they saw me in my office, I would be there trying to make computers work and to make either coding, debugging more than coding, sometimes running things and swearing at the computer. And the NASA in particular computers are getting harder and harder to use because they're obsessed with the security. So now every few days it wants to reboot itself because it gets a command to reboot, to apply updates and so on. So more swearing. But I wanted to show you a bit these things in practice then. And what's nice is that LIGO and Virgo have an open science initiative, have had for a while, that I was involved with starting up, but I left it before it got into detections, and so I helped release some data that was noise, basically. But it's now joined with LIGO. It's at GWOSC, the Gravitational Wave Open Science Center. Hoping the network works here. It worked before, so.
You don't have a network?
I had it before. Maybe it's just very slow. Okay, yeah. So from here you can get data releases, the actual strain data. You get event data. You can get posteriors for the so chains of parameters for the actual signals. And let's try some of it, right? Let's see. I'm a big Python aficionado, so I will not explain much of how, if you're not a Pythonista, of what's actually there, but just show you how very quickly with little code you can get to the physics, and hopefully maybe after this course you'll be curious enough to try to do to use some of this data for your own physics. So for instance, these are just packages. I'm going to download catalogs for the four LIGO Science Run. I'm going to merge them, and what a catalog is basically a table. Is it big enough? I can make it a little bigger. It's basically a table of all the events, and for each event you get a number of things, including estimates and ranges for all the parameters. So this is the content that we use to create, for instance, that visualization of all the events. And so this it's a database really. And so you can start making plots, looking at things. These are the masses. Mass 1 is always larger than mass in the rest frame. We could plot I think there's no D there. We could plot the chirp mass against redshift. We see the event that we see at higher redshifts up to 1 have larger chirp masses typically. We could plot the rest chirp mass against the luminosity distance, more or less the same story. We could try to see if there is, if I correct the chirp mass to the redshifted chirp mass, which is the one that actually sets the amplitude of the signal, and I plot against luminosity distance, I see again that there's a parallel almost relationship that I try to put in 5/3, right, which is what it should be. Should be minus 5/3, I guess. Okay. Oh yeah. Let's put in the axis. So PP X label. So red shifted the chirp mass, and PP Y label luminosity distance. The idea is that the strength of the signal is proportional to the redshifted chirp mass to the 5/3, and then luminosity distance is what it is. So the heavier systems we see almost proportionally to their amplitude. We can do more. Let's try to look at the strain. Okay, for this the first event. It takes a little bit of digging, the kind of programming that's not so much fun, but basically this database gives me the location of another file, which is a file here. It's a JSON file, which has just more details about this event. I was hoping to get rid of this, but So there are lots of things in here in this file about this event, masses and so on, but also more links to lots of files. Some of those are strain files that could be good. So I select a few just to be short and in the right file format. These are the URLs. You can automate all of this, right? So that's the thing. And then I'm just going to download them. And now these are HDF files. It's a rather general file for scientific data that's flexible. It's hierarchical. So this is the structure of a file. See, there's a meta section with just information about it. There's a section about data quality that actually tells me whether there were injections, so simulated signals, or in that data. It tells me other description of the data quality, and finally strain. Okay, so I can just grab the strain, use some of the metadata to build the time axis. So it tells me, the data set tells me when the data starts, the cadence, and the number of points. Okay, and let's, I guess I don't need this, but let's just plot it, and it looks like noise. Okay, well, not unexpected. This data goes to 4 kilohertz in terms of sampling, and there's lots of shot noise going up to there. This orange line that I plotted there is the location of the signal. So is there anything to see there? Maybe not. Let's obtain a spectrum. There's a standard function in Matplotlib to do it. You could do your own variant. It looks familiar. Okay, so these peaks here that you see are either the violin modes of the suspension. So a violin mode would be the fact that the string, if you pluck it, it makes a sound. And just like the strings of a string instrument, the quality is very high. So in other words, the oscillations tend to be very precisely at that frequency. And so is the thermal noise of that suspension. So that's what the peaks are, and there's no way to beat them down. Okay, you just take them, but you say, okay, they're very monochromatic, limited to that frequency. A few of these other may be hardware injections. So in some cases, one applies for either usually through light or maybe through capacitance. You apply an oscillation onto the test masses because it's useful to you to see how that input is translated onto the output. Okay, so that would be called a calibration line sometimes, and it's again, it would be there all the time. It would appear as a line in the spectrum. Okay, so we have the spectrum. We can use that to whiten the signal. Okay, whitening means that I'm going to reweight the Fourier transform of the signal by the square root of the power, which has the effect of evening out the contributions of different frequency bands in different frequency. If there's lots of noise at low frequencies, I whiten it, I bring it down to the same variance as the noise at high frequencies. Does this make sense? The match filter operation that we saw before is actually double whitening. You double both the data and the template, or you can think of it as whitening the data and then penalizing it even more because there's more noise than in some frequency than others. So, this code is a little bit technical, but basically I'm computing again the spectrum. I'm taking Fourier transform. Or I do something else. I do bandpass. So I'm going to cancel out all the noise below 20 hertz and above 350. Okay, because I'm saying that's probably most noise for the signal. And now plot the whitened signal. These are artifacts, just edge effects, but what's there? Okay, let's try to zoom in. I know the time of the event already, and here it is. Okay, so notice I've done very little to this data. I've just the whitening is reversible, in fact, and it's part of the data analysis, and I just did some band passing, and that's quite recognizable. You could almost do data analysis directly on that. You don't have to do a lot more to actually try to do your own parameter estimation. Let's look at the series for the other LIGO detector. And here it is. Okay, looks similar. And I can try to shift one of them and give it a minus and demonstrate the coherence between the signal in the two detectors. And that's what the 11-year-old student, who my wife points out was not blonde, but was actually Chinese. So I think I mixed her up with a different friend of my son's, had pointed out, why are the two signals shifted in the plot? They shifted because of speed of light. Okay, so if you want to do parameter estimation with modified gravity, whatever templates, the bar is not very high these days. The data is there. The sampling codes, there are lots of sampling codes available also to use. So and there are actually tutorials on this website on WOSC and elsewhere that go a lot deeper into doing this game. But the other thing you can do by digging into these files is to get the actual posteriors that LIGO did for you. The LIGO collaboration and Virgo collaboration did. And I wrote a little function that just does that, basically. It takes a little digging to find the location of these. But for instance, here I'm downloading the posterior for 170817, which was the first binary Newton star. And there are a few choices there. For instance, there are data sets for CGS-TLAO, PE, PyCBC. These are different pipelines that were used to analyze the data. I've chosen PE in this case, and PE offered also a variety of chains that you can download. This is this high spin and low spin that we were talking about before. So I think I chose low spin. And then a few more. And these are all the Newton star events. The result, they come through, again, these HDF data files. So it's downloading. Yeah, okay. Internet is not the faster, but I can show you in the meantime what they look like. So for instance, one of these, 170817, is again one of these pandas data frame. It's a big table, basically. It contains 8,000 entries, not a huge number, but it's a sampling from the posterior distribution. And for each record, you have the masses in the detector frame. So in this case, this analysis used the redshifting masses. You have some of the distance, position in the sky, inclination. Lambda 1 and lambda 2 are Newton star parameters that describe the quadrupolar deformability of the star, the love number, so to speak, spins and spin inclinations. Okay, and so from this you can make a figure that I actually have in my presentation, showing the histograms of, is it still going there? Yeah, it's still downloading. Well, the figure is, I lost it now, showing histograms of the smaller mass in all of these events. The nice thing is that if you want to do population level studies, they can be done starting from these posteriors. You don't need to redo your analysis of the individual events. As I was building this, I noticed it's a bit inhomogeneous. So some of the parameters names change between the first data release and the second one, and so on. So there's going to be a little bit of pain, but otherwise I think it's fun. It is very available. And okay, while this won't finish, but let me go back to the presentation. Play. Oh yeah, population inference, just what I was saying here. Now, let's say we have more than one event. We're going to think about these black hole and neutron star systems as coming from the same astrophysical population. And we want to try to characterize the astrophysical population based on the events that we have seen. In terms of my Bayesian, I lost my cursor. oh no, here it is. In terms of my Bayesian networks here, now I have a top level of population parameters that then generate the realizations of binaries that I detect individually. Okay, so if you do the calculus of probabilities, you can build the likelihood for all the events together, given these population parameters. You need to apply a weight for a model selection function. So for the fact that different models of the population will predict a different number of observations, because they may give us more high mass events that we can see, or more low mass that we don't see as far, and so on. So after you apply, but you can, most of this comes in with Poisson. It comes in with Poisson statistics, and it really simplifies to a product of the individual likelihoods, the individual posteriors, where now the prior for the source parameter are informed by the population parameters. It's like saying in the initial detection, we had to estimate mass. To do a Bayesian estimate of mass, you need a prior. You may say, okay, I'm going to take a linear prior, a uniform prior between 1 mass and 99 solar masses. Fine, you can do it that way. You get some results, you get a histogram for your masses. Now, however, we're instead saying this binary comes from a population where there's a power law dependence, a power law distributions of the masses with a certain amplitude and with a certain slope. So then the prior that I'm going to update with my likelihood is that astrophysical prior. And then how it's done in practice is that the chains that I showed are obtained with reference priors. So something simple, like I was saying, just a linear, maybe a uniform distribution or so on. So you can take those chains and you can reweight the likelihoods by the prior that you actually want. And the result is as if you were integrating the posterior against the astrophysical prior. Okay, is this clear? I felt there was lots of words with the same word in it repeated, but the big game is try to understand what the population look like. And so these are all the LIGO events, you know, on a mass plot. Some of the important ones are labeled. What can you draw out of it? So there's like a 70-page paper that the LIGO Virgo collaboration put out trying to do that. So I spent a couple of days studying it. And in truth, I mean, there's a lot of information in all this event. It's a bit of a free-for-all, meaning if there are many theories of astrophysical evolution of binaries, you can still pretty much fit any theory by changing its parameter to what's observed, because there are lots of clues in here, but they go in many directions. But one thing you can, just a basic thing you can see is to estimate the rate. Okay, we've seen so many events. We have an idea of how sensitive the detectors are that you get by doing simulated injections. Okay, to see how far you see, you take your data, you in software artificially introduce templates, waveform templates at a range of distances, and then you really do the parameters, you really do the detection analysis, and you see how many you get out. So that's really empirical. It's these selection effects are measured not on the strength of the signal, they're measured on the output of your varied pipelines, because you don't want to be sensitive to blind spots they may have or so on. That's what you observe. So the ranges are very very broad. Okay, so and they depend very strongly on what kind of assumptions you take for the distributions. So, for instance, if you model all the compact objects as coming from the same mass distribution, you get an estimate. If you separate the population and try to feed them independently, somewhat phenomenologically, and then bring them together, you get a different estimate, and so on. So wide ranges, but what's clear is that there are many more neutron stars that are black holes, but the black holes are much more detectable, like for this instrument. So the rates are larger for BNS. But in the events we detect, we get more neutron star black holes because the presence of the black hole make them so much brighter. And we have many fewer binary black holes, but they're so loud that we see them to a z of 1, and so most of the events are black holes. And if you try to do a mass spectrum, just a mass distribution, these are 4 different models assumptions. They all have a power law. They have they're somewhat adaptable to local features. So what can you say? Okay, so the rate really goes down with mass by a lot, right? This is logarithmic. Let's talk about black holes really. So there's a maximum at 10 solar masses, which is consistent actually with what we see with X-ray binaries and so on, which seems to prefer formation in the field, so in the galaxy, from a binary of 2 supernovae to main sequence star that then go supernovae and then merge. However, there's some evidence of substructure bumps at 18 and 35, right? Is that an illusion? Is that not small number, but medium number statistically unclear? These are unexplained so far. It's hard to get these peaks out of astrophysics. The other thing was that between 50 and 100 solar masses, there was expected to be no black holes. There were expected to be no black holes because of something known that I don't know a lot about, but called the pair production instability, which is kind of like a early supernova that flames out, that doesn't quite go all the way, but the star loses lots of mass to that, and therefore it's less massive to begin with when you have the actual supernova. But there's no evidence of this mass gap. It seems that there are black holes in this mass gap. Okay, so why is that? Is that because somehow this instability is not really there? Is it because these are black holes that form from 2 existing lower mass black holes in a dense environment, such as a globular or nuclear or active galactic nuclei, globular cluster, nuclear cluster, active galactic nuclei? Unclear, okay, at this point. But that's something that was expected, and the surprise is black holes were found there. Okay. Another thing that's surprising is that with this data set, instead of having just a rate that's constant in co-moving volume with increasing z, you can try to fit for the z redshift dependence of this variation, and you get a pretty steep dependence with increasing z, which is compatible with the star formation estimates, maybe a little higher. Okay, so let's go on to spins. Okay, spins. Yes. Question. Microphone coming. Yeah.
Is gap related to what you explained before? Or?
So there are 2 gaps. So the BBH gap is this gap between 50 and 100. The neutron star gap is the fact that you don't expect neutron stars heavier than 2.5, and you don't expect black holes lighter than 5. Okay, then you expect a gap there. There's also evidence that that gap is at least partially filled.
Mm.
Okay, so then this is the estimate for the density in that gap.
Okay, so for events that are in the gap regime, so those are
where one of the masses is there. Yes. So yeah, these are what this. It shows it's there. It's very small, but it says NS gap, for instance, is where the primary mass is between 2.5 and 5, and the secondary is a regular neutron star, let's say. So altogether, these rates point to probably a marginal stochastic background for advanced LIGO. Right after the first detection, there was a hope that there were enough black hole mergers that you could actually see a stochastic signal from all the ones that are too weak to detect, but you see it as a background. But it seems this would be more for like 3rd generation detectors based on these rates. Okay, spins are harder to detect, and this is really a free-for-all. I mean, I jotted down some notes because it goes in many directions. So for one thing, spin magnitudes, they're mostly small. okay, in geometrized unit. One would be an extremal black hole. One thing that's unexplained is that they're higher for higher masses, which is not, at least for field binaries, you usually wouldn't get, because higher masses lose more mass, so they should lose more angular momentum, and there should be less available to spin up the black hole. So that's surprising. If you actually plot them separately, separate the heavier and the lighter mass is actually compatible with 0, or it's lower, and the leading one is a bit higher. Perhaps not surprising. Tilt angles is interesting. So this is what kind of misalignment you have between the black hole spins and the orbital angular momentum. So it was thought that in field binaries, you have generally spins that are aligned with that are aligned by tidal forces with the orbital angular momentum of the binary. And therefore, that if you do observe significant spins, that's an evidence of formation in a dynamical channel, where existing black holes capture each other with the help usually of a third black hole. Given this finding, okay, that tilts are typical, one here would be alignment is still preferred, right? One is alignment, but anti-alignment, there's a disinfraction there. There's not a lot that are actually in the plane of the binary. That's, I think, is dynamically stable. So since these results were found, well, this assumption about formation in the field was revisited, because people say, well, for one thing, we have some optical binaries where there's evidence of a spin tilt in a field form binary. And also, maybe it was just the assumption was too strong, and even field formation can create tilt angles. What else? Effective in spiral spin. This one is a bit displaced from 0. Okay, so this would be alignment. A positive number would be alignment, and negative would be misalignment. This seems to speak against dynamical formation. In dynamical formation, you expect to have a symmetric distribution of anti-aligned and aligned spins. And there is finally some evidence for precession, as seen in the longer waveforms. This is the precessional spin, the tilt. One of the dominant spin and the tilt. This is a phenomenological parameter, as I was saying. I would say that there's maybe one binary or two where there's, if you look at the individual binary posteriors, there's evidence there for precession, but otherwise this comes from all of them together. It's never very clear in any one signal, but it comes from the distribution. Anything else I want to say here? No. Yes.
That there's more than one population mechanism that's at play at the same time and they contribute, or is it not very likely?
I think it's probably certain, but the way theorists work is that they try to explain everything, so that their model is the winner and so on. But we know there's formation in the field, we know there's formation in clusters, and we know there's formation even in AGNs, which is very, very interesting by itself. So they're all likely to be to happen together, but whether it's 50-50, 20-40, or 1-99,
right?
Okay, that may still be a win for one model. So too early to tell. There's one clue here that is missing, which is eccentricity. Okay, so you expect in this frequency band for LIGO, you expect signals to have circularized, because a loss of angular momentum is very efficient to gravitational waves. If you look at these in the LISA band, they should have you should see the residual eccentricity as a feature of the waveform, which actually generates higher harmonics. If instead of having things going on in a circle, they go on in an ellipse, you can do a harmonic decomposition and you get components at twice the orbital frequency, 3 times, and so That again is expected to be a clue of dynamical formation, the detection of significant eccentricity. But now maybe the field formation types will we come up with a mechanism to do it too. And there's always one way to get everything, which is a triple. Okay, you have binaries, you have triple. If you add a triple, it really shakes things off. We'll get more and more events, right? A factor of 10 between the first runs and the second one, factor of 8 perhaps, with twice the sensitivity. It will keep improving. Third generation detectors will see neutron stars much farther. So this is really the start. But you really got, the population theorists already fired up and writing. So, yep. Okay. Oh, neutron stars, right. So these are the posteriors for the individual events that have neutron stars. These two are well behaved, especially the one with, and it's not a lot, right? It's maybe 8, 2, 4, 6, 7 events. The pale ones are less certain. But from these, it looks like, one, the gap is filled. Okay, there are events where that straddle this gap, which will be the gray area here. And two, it points to a distribution that is not what was seen in the galaxy, in binaries, in pulsars, in recycled pulsars that are the ones that spun up to be very fast, and in slow pulsars, which instead have really two peaks. Double neutron star pulsars in particular have most of them have almost the same masses. People were thinking of using them as candles, actually, standard candles, because of this mass. Well, it doesn't look like that. This is much broader, and you can look at this at the gap. There are some here that are really suggestive. So there's a binary. Which one is it? 20, 0 to 10. That peaks, that goes beyond 3 solar masses, peaks above 2.5 in terms of mean. Is that an extension of the Tolman-Oppenheimer-Volkoff limit because of physics, nuclear physics, or is it a very light black hole that somehow formed there? Is it a primordial black hole even, which can form at any mass unbound by physics? And what about this guy here? So this guy has masses of 22 and is that the, yeah? So this is the very heavy one. So this one is strange enough that you can show it's an outlier with respect to the rest of this distribution. So if you exclude it from building a joint population, you get a very different result, and therefore the rest of the detection don't predict it. It looks strange with respect to them. So I'm not sure what the conclusions are in terms of physics, but it stands apart just on a phenomenological basis. Okay, so let's see what my time is. I can probably do this quickly. So I wanted to show you a different flavor now, data analysis, which is how we do data analysis with pulsar timing. This slide I showed you already is how you take pulses obtained by averaging out individual pulses. You do this complicated deterministic model, get out lots of parameters about the binary, its position, and so on. And you get down all the way to a residual that either may have gravitational waves or, for instance, encodes a change in the orbital period due to gravitational wave emission. What's the premier source for this? It's supermassive black holes, okay? Not a million, but a billion solar masses at the center of the largest galaxies, where they have merged, they found each other, and they're orbiting and producing gravitational waves. And most of them we think will be far enough that they will be not evident as individual sources in the pulsar timing data set, although some may be if they're close enough, but we will generally see them as a stochastic background. There's a theorem that I will try to get through due to Finney that shows that when you have a population like this over a range of redshifts, all that matters really is the power, is the frequency domain dependence of energy loss, okay? And that alone sets the overall power law for the entire population. Basically, each black hole is emitting, it's doing its own in spiral, going up in frequency and so on. If you see that in the frequency domain, it's a downward slope because the amplitude is going up, but it's spending less and less time at higher frequencies. If you take an ensemble of those, you're going to find them at all frequencies with the same distribution of power of a single one. Okay, so it's a bit like the population as a whole repeats what the individual does. That means we're looking for a stochastic background with a very characteristic slope for gravitational waves. The way you do it is using an array of many pulsars, looking for a correlated signal between them. In particular, the signal on the Earth is hit by gravitational waves coming from all directions at the same time. The timing of the pulsars in all direction feels that effect at the same time, except with different geometry, because the line of sight is projected onto the pulsar polarization. This is what the data set looks like. These are 10, 15 years. Here we've already taken out a best fit estimate of all the timing model parameter, position, frequency dependence, and so on. It should look white if there is some kind of residual time dependence. That could be gravitational waves, in fact, or that could be a pulsar intrinsic process due to the fact that the spin is changing, or so on. To decide which one it is, you want to see whether these shapes are compatible in different pulsars. Okay, that's the game. So you build a bit like, you don't work with templates, right? Here we're trying to describe a stochastic signal. We don't know the shape in advance. So what you do is you build a model of your residuals, which includes measurement noise, which includes errors in all of these timing model deterministic effects that I was telling you about, and that includes Fourier components for the stochastic processes, both the intrinsic ones and the ones that would be gravitational waves. So a huge linear model, basically. Okay, a huge linear model where all these basis vectors have Gaussian distributed amplitudes. That's one definition of a finite dimensional Gaussian process. And again, I was saying, I don't know if I said it already, but the universe can be described as a collection of linear oscillators. I think that's what the field theorists would say, even, and so I agree. And so can this system. See, it's the model. And now the Fourier components for the gravitational waves are correlated. They come from a given spectrum, a simple parallel, for instance, and the correlation is a function of the angular separation between the binaries. If a binary with itself is obviously have a correlation of 1, two binaries in exactly the same direction have a correlation of 1/2, because half of the signal comes from the gravitational wave hitting the pulsars, and that's typically separated by many kiloparsecs or hundreds of parsecs, and so it's incoherent. But the part that hits the Earth is coherent. And now, two detection approaches. Okay, one is Bayesian, and is the idea of Bayesian model comparison. So the idea, I can build those networks again for two models, and I'm going to integrate the likelihood of the data given that model against the prior for the parameters. And I'm going to do the same thing for the other one and take the ratio. So this is a base factor. It links to the idea of betting odds, okay, gambling with things when you're sure about what's happening. And you can try to do that. And if you do it between two models for pulsars which either have no gravitational waves or have an amplitude of gravitational waves that's uniform in logarithm, you get compelling evidence that the pulsars are seeing the same process of the same amplitude and of the same power law. Okay, there the base factor is of order 100,000, 10,000, and so on. The next step, however, is that you're going to, and that's a possible posterior distribution of that parameter. However, what you really want is a signal that's specific to gravitational waves, and that's a signal where it's not just the strength and the power dependence of the excess noise, excess residual that is compatible, but also the shapes with this Hellingsdown, Helling-Downs correlation function that I was showing you. And that for the last public nanograph data set is still inconclusive. Okay, so the base ratios are of order a few. It's like mildly, and there's no evidence for different correlations. So this is a different approach, right, to detection that the idea of a likelihood ratio using optimal filtering, vignette filtering, where you have the templates. Here you have models that try to explain everything that's in the data, including what you really want, the gravitational waves, but including things like what actually is the position of the pulsars, which I know imperfectly, or sources of noise like the electrons in the galaxy going out of the pulsar that give me a dispersion of the signal. The other strategy you can do is hypothesis testing. And this is from your standard textbooks, is the idea that you build a statistic, a bit like the signal to noise I was showing you before. You want to compute the background under a null hypothesis. So if, let's see, if nothing happens, if the drug you're studying has no effect, the vaccine has no effect, what kind of distribution you expect of your outcome, in this case, the statistics. You compare that with the value actually observed, and this gives you a p-value, which is not the probability of a hypothesis given the data, is the probability of the data given the null probability. Okay, but that can lead you to reject the null, and that would be detection in our case. Same plot as before. So that you can do for pulsar timing by building a statistic of the data. This is one number that I get out of the entire data set, which actually is by design built to extract only the geometrically correlated signal between the pulsars. And it's built so that it's actually proportional to the power in the gravitational waves. And so then this is quite different than the Bayes factor detection. This is more like, it's more similar to LIGO in a way, more classical. You're looking at comparing two hypotheses. And that, for the moment, is also inconclusive in nanograph, but it will be the thing that tells you this is a 3 sigma, 4 sigma, and 5 sigma detection. Okay, and if you break it up, the statistic into bins of angular separations, you should get a shape that recovers this Hellingsdown correlation function. And so that's 12.5. Does this shape fit that? If you squint a bit, there's an outlier there and there. It's a little bit too high. In fact, I was in 12.5 year data set, there's evidence of a monopolar signal. So a signal that hits all the baseline, pulsar baseline coming to Earth with the same fluctuation, which you get, for instance, if your clock, the UTC, let's say, had a wander. Since we were talking about the building the background and the idea of time slides, right? How you empirically evaluate the background due to noise in LIGO. You cannot do it here because you don't have any more data than you're using. So you want to see a signal in the entire data set. You cannot do time shifts. But people have come up with the idea of, really the best one is the idea of randomizing the phases. So this reconstruction in Fourier domain of the signal that I use to compute the likelihood, if you just throw in random complex phases at all frequencies, that has the effect of removing all spatial correlations between the pulsars, because they're all randomized. So you can use that to build the background. And if you look at what the measure statistic on top of that has a p-value of maybe 0.1, which is not very compelling. Okay, so we can talk more about it if you want, but basically that's where the 12.5 year result was left. Detection of a common amplitude and common spectrum signal. No evidence for the spatial correlations. Somewhat slope that's compatible with gravitational waves. In these units, it would be 4.33, a little bit on the edge. Okay, so that's it for today. That was fast, I know, on the pulsars, but I wanted to give you basically a different flavor of data analysis and how it fits in both a Bayesian and a classical statistic hypothesis testing framework. Okay. I made 12:00. Which means I have no leftovers for next week. So, any question, or you're ready for lunch? What's for lunch? Question.
So, questions from the virtual room?
And look, the CO monitor is down, so something worked.
So no questions? Sure.
Or maybe one. When you explained on your Python, the whitening, that look quite impressive to me, because it seems you did not need to use a waveform to recover the signal. Is that right?
Yeah, and there's a good fraction of these black holes that are so loud, effectively, that just band passing is sufficient to make them stand out. And maybe I said it already last week, but when people in LIGO and Virgo saw that shape shortly after the detection, that was very convincing. And they had to wait for the statistical evidence, because they had to wait to collect enough data to build up the background at the 5 sigma level. And they actually ran the experiment until they got 5 sigma. so they went the other way, which is not cheating. It was going up all the way. But you know, if they'd run another 6 months, they could have gotten 6 or 7, basically. But when they saw that waveform, that was very convincing, because it seems very specific to. The only really other explanation would have been a hoax of sorts, or the fact that somehow the injections had been made into the interferometer to simulate such a signal. But so there was actually an internal inquiry into into that, which looked even at things to who had access to the various experiment rooms at what time and so on, because you'd have had impossible mission level kind of Mission Impossible, sorry, level kind of thing. You could have a little gadget with like an iPod with a little transducer. You plug it into the right place into the thing. You arrange it to be simultaneous, and so they even looked at that, right? Evidence of tampering and so on. So yeah, but otherwise that shape was very specific. And one of the problems we have in now with next data releases for pulsar timing, we should have enough sensitivity, just based on the length and the characteristics of the data sets, to see correlations with some statistical certainty. So we hope and expect to have it, but we don't have anything like a killer thing like that waveform to show. What you can show is the spatial dependence of correlation, and that's the best we have as a waveform. And I think that's all right, because we do think there are binary black holes in most galaxies. We do think they merge. That signal, the stochastic signal, is really expected to be there. So it's confirming it can be done as a matter of or statistical certainty. But anyway, I'm giving a talk at IAP on the 23rd with many more details about this. So and that will be probably on Zoom also. So you can, if you're on the right mailing list, or I can forward this list if you want.
So
yes.
When will you announce? So when will be the next?
So we have a deadline that we'll miss for the 3 international pulsar timing array big consortia, US, Canada, Australia, and Europe, to finish jointly by the end of 2022. I can easily see sleeping 6 months just because international. If internally we're doing okay, I think, but internationally it may be harder to achieve. But yeah, 23. And but the result may be 2.5 sigma. You know, it's I don't know exactly which then is not quite a detection, right? It's the question is taking account all systematics and so on, whether we can really make the achieve the potential significance of the potential sensitivity of the data set. And yes.
Question?
Good. See you next week. Thank you so much.